An early thermometer is based on a reservoir of ideal gas connected to a manometer as shown below. What physical property of the gas is directly related to the temperature? So this is, we don't really see, I think, thermometers like this in common usage today. In fact, I think most of us are used to digital thermometers, so we've come a long ways. It's maybe similar into how thermometers based on liquid like mercury would work, in the sense that there's some material in the thermometer that's going to have some property of it change. Maybe it's going to expand in some way, right? In response to whatever object's temperature is being measured. And in this case, this container of water here is really the thing that we're measuring the temperature of, and the kind of thing that in the early science of thermometry, like that somebody would do, is they would probably use water that's close to freezing and then water that's boiling to calibrate a thermometer like this as part of their construction of it. Getting back to the question, though, what physical property of the gas is directly related to the temperature of the thing being measured? So the idea, again, is like we put it in contact with that. You probably wait a little bit to make sure that the gas and the water come into thermal equilibrium. But once they are in equilibrium, like, what do we expect the gas to do? And maybe a simple answer to this, we're going to look a little bit later in some more detail, but I often assume that everyone probably at some point has seen the ideal gas law. In other words, PIV-NERT, as I like to sometimes call it, or PV equals nRT, right, where it's pressure times volume is equal to the number of moles times the ideal gas constant times the temperature. That actually has to be in Kelvin. One of the more basic gas laws that actually, this one you could argue came from, I mean, this formula kind of summarizes everything for an ideal gas, but before it was realized you could do this, there were some more basic ones. And one of them was that for constant volume, pressure is proportional to temperature. And that might make sense from this formula. If volume is a constant value, if N is a constant value, in other words, a fixed amount of gas, and R is a constant because it's the gas constant, then pressure would be proportional to temperature. And in this case, how that relates is that as the temperature of this gas changes, the pressure in here changes. Now, you could say, is the volume exactly a constant? I'm going to assume that this tube is very, very thin. So even though it's pushing on some liquid here in the manometer, that's not going to represent a huge amount of volume change. But the reason why this liquid is not at the same level on both ends is because maybe there's higher pressure in here than there is out here, where the tube kind of opens up to the atmosphere. So based on that, the answer I really have here is that it's pressure that is directly related to the temperature. So let's go and check out how that works with the answer in the slide, because it says the gas pressure is directly proportional to the temperature relative to absolute zero. In other words, this has to be in Kelvin. So it says here, such as is measured on the Kelvin scale.